In this tutorial, I'm going to talk about adding two oscillatory quantities together. Here's the thing we're going to add together: cosine of omega t plus phi 1 plus cosine of omega t plus phi 2. This is a very important thing in optics, where you might be adding two beams together of the same frequency but with different phase offsets, so you get an interference phenomenon. In Optics 262, we really care about this because you can solve it using real numbers or using complex numbers, and the point of this exercise is to emphasize that complex notation is a really good way to solve this problem, and even harder problems, it's even more advantageous to use complex numbers. So let's get started. Here's the sum of two cosine functions we want to add. They have the same frequency omega, but they have different phase offsets, phi 1 and phi 2. Now, how would we simplify this expression using real numbers? So if we are dealing with real numbers, the way that this gets simplified is to notice sort of a trick. I see that this is cosine of something plus cosine of something else, and there's some similarity in the arguments, so I make use of the following thing. I know that cosine of alpha plus beta, just in generic form, alpha and beta don't mean anything special here, that is a trig identity that you should have memorized or readily available. It's equal to cosine alpha cosine beta minus sine alpha times sine beta. And what's neat is that the cosine of alpha minus beta equals the exact same thing here, but plus sine alpha sine beta. So when you add these two things together, you just get 2 cosine of alpha cosine of beta. So now we've got the sum of two cosines equaling the product of two cosines. So to keep going with this, you have to now say, okay, well, alpha, I have to figure out what alpha and beta are equal to. And then you have to make sort of a clever observation that if you say that alpha equals omega t plus the average value of those two phase shifts, and if you say that beta equals the difference in the phase shifts, phi 2 minus phi 1 over 2, then, and we'll define that to be delta phi over 2, alpha and beta this way, you can then rewrite the initial expression up here. You can rewrite this initial expression. The first term actually becomes cosine of alpha minus beta, and the second term becomes cosine of alpha plus beta. And then you can immediately say that that answer is, of course, 2 cosine alpha cosine beta, and then you can write out the answer as 2 cosine of plus what we would call, I'll just write it out, phi 1 plus phi 2 over 2, and then cosine of delta phi over 2. And we sometimes even will write that physically as twice the cosine of omega t plus the average phase shift times the cosine of half of the difference in the phase. So there's our answer right here. And now we want to ask ourselves, can we get that more easily using complex numbers? So let's see if we can do that. So that was the real way. Here's the complex way. Now in this time, we take that cosine of omega t plus phi 1 and we rewrite it. We say that the cosine of omega t plus phi 1 equals the real of e to the I omega t plus phi 1. Of course, we say the same thing for phi 2. That's there. So we add those two things together. So the sum is just going to be the real of the two things added together. E to the I omega t plus phi 1 plus e to the I omega t plus phi 2. Now we can just take what's running around in here in the interior, and that's a complex number expression. We can then start modifying that as complex numbers. And notice something really nice happens there. So I'll just continue to have a real number expression here, but on the inside, what's that become? I can factor out an e to the I omega t from both terms. And what have I got left? It's times e to the I phi 1 plus e to the I phi 2. Now we still have to do a little bit of manipulation. We recognize that this expression looks like something like the definition of cosine, e to the I phi 1 plus e to the I minus phi 1. But not exactly. We have to factor out a certain factor for that to be there. So the one tough math trick on this step, so we notice that this expression left over here looks a lot like the definition of cosine. If we could only write this as e to the I phi plus e to the I minus phi, that would be very simplifiable to a cosine. And we can do that. We just have to factor out the right value. And to figure out what that value should be, it's not that different from the previous one. Imagine we sort of have a number line here, and we have a value for phi 1 and a value here for phi 2, and we want to take the midpoint, the middle value there, which would be the value of phi 1 plus phi 2 quantity over 2, which is what before we called phi bar over here. Now the distance between these 2 points, phi 2 and phi 1, if I draw an arrow like this, I could call that value delta phi, and the value from the midpoint to each of the outerlying values would be delta phi over 2. So this value over here I can write as phi bar plus delta phi over 2, and this becomes phi bar minus delta phi over 2. Notice now that I've got a minus delta phi over 2 and a plus delta phi over 2. That's sort of what emerged over here as well. I can now rewrite our expression up there as the real of, okay, I already factored out the e to the I omega t. That was the easy part, and it's the benefit of using complex numbers. Now I'm going to factor out an e to the I phi bar also. And now what's left? It's just going to be e to the I phi 1. Well, phi 1 is phi bar minus delta phi over 2. E to the minus delta phi over 2. E to the I delta phi over 2. And phi 2 is how much more than phi bar is it? It's positive. E to the plus I delta phi over 2. So now I can immediately rewrite this as just being twice the cosine of delta phi over 2. Notice that that's emerged over just like it was over here. The other two terms can be grouped together as e to the I omega t plus phi bar times that. And we're taking the real of this whole expression. But you know what? This thing at the end is already real. So it can come outside of the real operation. It's a real number, just multiplying. And when I take the real of what's left in there, lo and behold, the real of an e to the I something is just a cosine. So that becomes cosine of omega t plus phi bar. I'll put the 2 out in front from here, and then I've got cosine of delta phi over 2. So now this expression that I've just derived exactly matches this expression over here. So to summarize, you can solve this particular problem either way, but the advantage of going to complex notation and writing oscillatory terms as complex exponentials is that this oscillation omega t frequency can be factored out very naturally. Both terms oscillate at the same frequency. In optics, we would say these are two beams of the same wavelength. So we factor that out easily. What we're left to simplify is pretty simple. E to the I phi 1 plus e to the I phi 2. You do a little bit of intuition about how to make that into a cosine term because it looks like e to the I phi plus e to the minus I phi. And you get another term that factors out, and these two combine very naturally to make a cosine. And what's left behind combines to make a cosine, and you get the product of two cosines. In the real problem, you really kind of needed to know a trick for simplifying this. You needed to think about cosine alpha plus beta and cosine alpha minus beta. They add together in a way that cancels out the signs. But then you have to figure out what alpha and beta are, and then it kind of comes out this way, and it's not as easy to do it. Once you get good at converting things to complex numbers, getting to these sort of steps becomes pretty easy.